Welcome back to the show, everyone. Today, we're diving deep into the world of large language models and exploring a groundbreaking research paper that offers a novel approach to boosting their performance without relying on ever increasing model size. Joining us is a lead researcher on the paper from DeepMind, and field expert name, a leading expert in natural language processing. Thanks for being here. It's a pleasure to be here. Thanks for having me. We're thrilled to have your insights as well. Let's jump right in. Could you start by giving us a brief overview of the paper's main topic and the historical context that sets the stage for this research? Absolutely. The paper focuses on a novel technique called Retrieval-Enhanced Transformers, or RETRO for short. It tackles the challenge of scaling language models without significantly increasing their computational cost or model size. Now, you've probably heard about the remarkable advances in language modeling in recent years, thanks to massive transformer models like GPT-3 and Jurassic 1. These models have achieved incredible performance on a wide range of tasks, but they come with a hefty price tag. Training them requires enormous computational resources and massive amounts of data. This poses a significant barrier to further progress in the field. So, the paper proposes a different approach, focusing on retrieval. That's a pretty powerful concept. Could you elaborate on that for our listeners? Exactly. Instead of solely relying on scaling the model itself, Retro leverages a massive text database as an external knowledge source. It conditions on document chunks retrieved from this database based on their similarity with the preceding tokens in the input sequence. Think of it like giving the language model access to a vast library, allowing it to draw upon information that goes far beyond its training data. This is what we call a semi-parametric approach, as opposed to purely relying on the parameters of the model. It's fascinating. This approach could potentially unlock new levels of performance and efficiency. What are the key innovations and contributions of this paper? The paper introduces several key innovations. First, they introduce this Retrieval-Enhanced Transformer, RETRO, model architecture, which seamlessly integrates retrieved text chunks into the model's predictions using a novel mechanism called chunked cross-attention. This mechanism operates on a chunk level, dividing the input sequence into smaller units and retrieving relevant information for each chunk. The beauty of this approach is that it maintains linear time complexity with respect to the retrieved data, making it computationally feasible to handle massive databases. That's a crucial point, Doctor. Linear time complexity means that the retrieval process scales efficiently, even as the database grows exponentially. This is a significant improvement over traditional methods. Absolutely, and it gets even better. The paper also introduces the concept of a frozen BERT retriever. This means that they use a pre-trained BERT model, which has already learned to encode text into meaningful representations to identify relevant chunks from the database. This eliminates the need for training and updating the retrieval network, significantly reducing computational costs and allowing them to scale the retrieval database to an unprecedented level, trillions of tokens. That's remarkable. To put it in perspective, the database they use, called Massive Text, contains over 5 trillion tokens. That's an order of magnitude larger than the datasets used for training traditional large language models. Could you comment on the significance of this scaling in the context of previous research?
It's a game changer. Prior retrieval-based language models, like KNN-LM and SALM, were limited to databases of billions of tokens at most. Scaling up to trillions of tokens opens up entirely new possibilities for language models to access and leverage a much broader spectrum of information. It's like expanding the model's memory capacity dramatically, allowing it to draw upon a far richer knowledge base.
That's a great analogy. And beyond just the sheer size of the database, the paper also introduces a novel evaluation methodology that's crucial for understanding the true impact of retrieval. Could you explain this leakage-aware evaluation approach? Certainly. One challenge with retrieval-based models is the potential for test set leakage. This happens when the evaluation data contains chunks that are also present in the training set, allowing the model to simply copy them rather than truly generalize. To address this, we introduced a method for filtering out evaluation chunks that have a high degree of similarity to the training data. This allows us to assess the model's performance more accurately, focusing on its ability to generalize to truly novel information. That's a very insightful approach, Doctor. It helps to separate the model's ability to exploit existing knowledge from its ability to generalize and learn new information. Have you seen this approach used in other language modeling research?
It's a relatively new development, but it's crucial for evaluating retrieval-based models. Researchers are starting to recognize the importance of addressing test set leakage, particularly as we're dealing with increasingly larger and more diverse data sets. This approach can help to ensure that performance gains are attributed to true generalization rather than simply memorizing the training data.
Let's move on to the methodology of the paper. Doctor, could you walk us through the retro model architecture, explaining how it works step by step? Okay, so imagine you have an input sequence. The retro model first splits this sequence into chunks of a fixed size, let's say 64 tokens. For each chunk, it retrieves its k nearest neighbors from the database. These neighbors are selected based on the L2 distance between the BERT embeddings of the chunk and the database entries. The BERT model is used because it's already trained to encode text into meaningful representations, and it's frozen, meaning it's not updated during training. This makes the retrieval process extremely efficient. So the model is essentially looking for chunks in the database that are semantically similar to the current chunk, right? Exactly. And once it retrieves these neighbors, it feeds them into a bidirectional transformer encoder. This encoder processes the retrieved chunks and outputs encoded representations of their meaning. Now, these encoded representations are where the magic happens. They're integrated into the main transformer decoder using this chunked cross-attention mechanism. Could you explain what chunked cross-attention actually does? Think of it as a way for the decoder to focus on the most relevant information from the retrieved chunks. The chunked cross-attention layer calculates attention between the encoded neighbors and the decoder's hidden states, allowing the model to dynamically adjust its predictions based on the retrieved information. Essentially, the decoder can selectively attend to parts of the retrieved chunks that are most relevant to the current context. And this whole process is done in a way that preserves the autoregressive nature of language models, meaning that the prediction of each token depends only on the previous tokens and the retrieved data from the preceding chunks. This ensures that the model's predictions are consistent with the order of the input sequence, right? And that's what makes this method so powerful. It allows the model to access a much larger context than traditional models without compromising its ability to generate coherent and grammatically correct text. This is a really interesting approach. It's very different from previous methods that focused on simply adding retrieved information to the model's predictions, like continuous cache or KNN-LM. Those methods relied on interpolating between the model's output and a probability distribution based on retrieved tokens. Retro takes a more integrated approach, allowing the model to reason about and leverage the retrieved content directly during generation. Could you comment on how Retro's approach compares to other retrieval methods like RAG and PHI-D?
You're right, it's a significant departure from those earlier methods. RAG, for instance, relies on a retriever trained separately from the generative model, which can lead to misalignment between the retrieved information and the model's output. FID, on the other hand, trains the retriever and the generator end-to-end, but this requires searching the database during training, which limits its scalability. Retro's use of a frozen BERT retriever and its integration of retrieval into the pre-training process make it both more efficient and scalable. It allows the model to learn how to effectively leverage retrieved information during generation, which is crucial for achieving high performance on knowledge-intensive tasks. Moreover, the chunked cross-attention mechanism, as you mentioned, enables the model to selectively attend to the most relevant information from the retrieved chunks, making it more precise and adaptable.
That's a very insightful comparison. It seems that retro strikes a balance between efficiency, scalability, and effectiveness. Now let's move on to the paper's experimental setup and results. Doctor, could you tell us about the data sets used in the experiments and the metrics used to evaluate the model's performance? Sure. We trained retro models with various sizes, ranging from 172 mem to 75B parameters, and evaluated their performance on a range of language modeling benchmarks. These included C4, Wikitext 103, Curation Corpus, Lambda, and the Pile, which is a massive dataset of diverse text. We also created a special dataset consisting of manually selected Wikipedia articles that were added or heavily edited after our training data was collected, to ensure we were evaluating the model's performance on truly novel data. To measure performance, we used bits per byte, BPB, which is a tokenizer-agnostic measure of the model's ability to compress the data efficiently, as well as perplexity and accuracy, depending on the specific task. So, you were essentially testing the model's ability to predict the next token in a sequence, right? And you were comparing the performance of retro to baseline models of similar size without retrieval. Exactly. And we found that retro consistently outperformed the baseline models on all the data sets, demonstrating the effectiveness of the retrieval approach. Moreover, we observed that the performance gains of retro did not diminish as we scaled up the models, indicating that retrieval is an effective strategy for enhancing performance at various model sizes. That's a significant finding. It means that retrieval is not simply a workaround for smaller models, but a powerful tool that can be used to boost the capabilities of even the largest models. And what about the impact of scaling the retrieval database? Did you see any improvements as you increased the size of massive text? Yes, we saw a significant improvement in performance as we scaled the database size. We found that the model's performance increased dramatically as we added more data, even at evaluation time. This highlights the crucial role of having access to a vast knowledge base for improving language model capabilities. That's really compelling evidence for the power of retrieval. Could you comment on the implications of these findings for the field of language modeling? Where could this research take us?
This research has profound implications for the future of language modeling. It demonstrates that semi-parametric approaches, where models leverage external knowledge sources, can be a highly effective alternative to solely relying on parameter scaling. By augmenting the model's capabilities with a massive text database, Retro opens up exciting possibilities for building more efficient, scalable, and powerful language models. This could lead to a paradigm shift in the field, moving away from the constant pursuit of ever larger models and embracing a more data-driven approach.
That's an exciting prospect. It's not just about building bigger models, but about building smarter models that can learn from a much wider range of information. Did your experiments reveal any unexpected outcomes or limitations of this approach? We did uncover some interesting findings. One unexpected outcome was that the performance gains on tasks like Wikitext 103 were more substantial than expected, suggesting that Retro effectively exploits overlaps between the training and evaluation data, even when the actual evaluation documents have been removed from the training set. This indicates that the model can effectively learn to generalize from similar contexts, even if they are not exact duplicates. However, as we discussed earlier, there are limitations to this approach. The retrieval database, while massive, may not cover all possible domains or topics, limiting the model's ability to retrieve relevant information for certain tasks. Also, the reliance on a frozen BERT retriever can hinder the model's ability to adapt to new information or evolving contexts. Fine-tuning the retriever could potentially improve performance, but this might introduce additional computational overhead. Finally, the leakage-aware evaluation methodology, while helpful, does not completely eliminate the issue of test set leakage. Further research is needed to develop more robust evaluation methods that mitigate the impact of leakage. Those are important points to consider. It's clear that there's still much room for improvement and further research in this area. What are some potential future directions that you see stemming from this research?
I think there are several promising avenues for future research. One area to explore is fine-tuning the BERT retriever to improve its accuracy and adapt to new information or evolving contexts. Another is to investigate the use of different retrieval strategies, such as sparse retrieval methods or those based on latent topic models, to further enhance model performance and broaden the scope of retrievable information. Developing more sophisticated methods for filtering test set leakage, potentially employing techniques like adversarial training or knowledge distillation, is another crucial direction. Finally, we need to investigate architectures that more effectively incorporate the retrieval encoder's outputs into the decoder's predictions, enabling the model to more effectively leverage the retrieved information for generation.
Those are very insightful suggestions. Let's shift gears now and talk about the broader impact and potential applications of this research. How do you see Retro's capabilities affecting other areas of natural language processing and beyond?
Retro's ability to leverage external knowledge sources could revolutionize various fields, from open domain question answering to dialogue generation, text summarization, machine translation, code generation, and even knowledge graph construction. Imagine a language model that can access a vast library of information and provide accurate and informative responses to complex questions, generate engaging dialogue, or even write creative content. This research could pave the way for more sophisticated and insightful AI systems that can interact with the world in more meaningful and informative ways. It has the potential to revolutionize how we interact with information and how we generate content, bringing us closer to a future where AI can truly collaborate with humans.
That's a very optimistic and inspiring vision. Dr. Uri, do you have any final thoughts you'd like to share with our listeners? This research is just the beginning. We're excited to see how the field of language modeling evolves as we explore the potential of retrieval-based approaches. It's a promising direction for building more powerful and efficient models that can leverage vast amounts of information to generate more insightful and informative text. We believe that by combining the power of deep learning with the vast knowledge available in external databases, we can unlock new possibilities for language models to contribute to a better understanding of the world around us. Thank you both for sharing your expertise and insights. This has been a fascinating journey into the world of retrieval-enhanced transformers, and we're excited to see what the future holds for this innovative research. To our listeners, make sure to check out the resources and links provided in the show notes. And join us next time for another deep dive into the world of cutting-edge AI.